Today we're going to look at position triggered outputs. Now, all the drives have software triggered outputs. Add a position, fires an output. Software is limited to update rates and configuration times. I like to say about a millisecond, maybe a little better. Outputs are turned off and on at the position loop update rate. Some drives have 333 microsecond, other drives have 250. So it's not very fast, but it's effective. So I got a motor here with 4096 counts per rev, and I want to configure an output once per rev, like an index to pulse. So I go to the input-output screen and configure an output, custom position triggered output, and then there's the configuration screen. So trigger at position 1024 and leave it on for a millisecond. That's a nice long pulse. And again, it's probably plus or minus a millisecond, maybe a little better, maybe 333 microseconds times 2 or half a millisecond on a plus drive. So that's the basic software configured output, and you can do this on practically any output. Now, some outputs are much faster than others. So if we choose an output on a Xenus Plus drive, say a XEC Xenus Compact, I see out4 as a high-speed output. And this is just your basic TTL kind of level, 74 ACT, 1G 125. And you can turn it off and on, and it's fast. It's really fast. So let's take a look at how we can make use of this in the Plus drive. We want to look at the hardware triggered output. And the hardware triggered output does not use software to do it. It's embedded in the FPGA code. So it's just a digital circuit. So we have triggered outputs at position. And there's a description here. Hardware. These are all the fancy modes of operation for output triggers. But this is a hardware triggered, and in the latest firmware, you can configure an output. 0x71 is out 1, which is output 2. So the software says one thing, the parameter dictionary says another. So 0x73 would be out 4. So if I wanted to configure the output to be hardware triggered, I want out 4. That's a fast output. And I want to configure 0x71 in mode 16. So we just write the decimal 16 down to the drive. So that's what I did here. Just wrote down to the drive. Bypasses this stuff here. You can write this to flash too. But the other parameters, they're in RAM. So these have to be configured typically before you make your move. But if your move's constant, like a linear slide from one end to the other, you want to fire, so many pulses after a certain position, then we can do that. So for the first example, we're going to look at 0x185, and this is the way we configure the mode of the drive. So the configuration parameter is configured based on what mode we're going to use. So there's a dual compare mode, a single compare mode. So dual compare is configure 1. Single compare is mode 9. And this is a description about the interpolated output pulse positions. We'll take a look at mode 0 first, configuration of 1. And for this, I'm going to set the two values the same. So at that position, In the case of value 0 and value 1, registers are configured with the triggered position. The increment is set to 0. So the increment I'm going to put to 0, and these two I'm going to put at the same value for value 0 and value 1. Trigger single position, simply set two trigger values at the same value. So I'm going to do that. So I'm going to set 185 equal to 1. Oh, that's in RAM only. 187, I'm going to set to 1024. 188, I'm going to set to 1024. The increment, no more, just let it fly at that position. And then 18A, let me get the value that's in there now. This is a really big number here. This is the time compare pulse period. The lower 20 bits of this parameter give the period of the compare output in tens of nanoseconds. So if you could measure a 10 nanosecond pulse, you could set it to 1. My oscilloscope can't quite go that low for a captured trace, so I'm going to use like 10 microseconds or maybe 1 microsecond. So yeah, 186 is the status, so we can read that. These two values are used to configure the positions, and the compare increment is used in some modes here. So those are the parameters that I was setting, and that's how they're defined. So to keep things simple, I'm going to start at the 0 position where my index is occurring, and you can see the accuracy of the index position here. It's pretty close. It transitions, and you know, for display purposes, it's okay. I've got my pulse at position, so as I run, start generating a pulse, and I've got a very high speed, short time, 62 microsecond sample rate, and I need that to get all the points. But even then, as I decrease the pulse period, it starts to get really small, and eventually I'm not able to trigger it at all on my output. It's kind of a random catch for the scope, but it really is coming out of the drive, and we'll take a look at that on the oscilloscope, and we'll see how accurate that is with respect to position. And what you'll see is it's like nanoseconds. The thing has no jitter, and it's pretty stiff, so this is good for like a laser pulse at a specific position. Okay, so I've got my oscilloscope here that's connected to my encoder B. So I'm going forward and reverse 1 rev on the motor. This is a little Comorgan AKM motor connected to a Zenith compact. I've got the serial port here so I can talk to it, the stow jumper so it can enable. I got 24-volt keep alive, AC power, motor wires, and that thing's configured to go several thousand RPM in 1 rev, so extremely high accelerations, low inertia. You may not be able to see the shaft rotating, the tag on it, but you can see the motor jiggle every time it goes forward or reverse. So what I'm doing is I'm triggering on this pulse here, which is a very long pulse, so it's triggered, but the frequency is set so I can capture the kilohertz signal that's coming in on the encoder. At very high speeds, it could be megahertz. But so this parameter 18A sets the pulse width, and we can see it in the scope here. When we start reducing the pulse period, we can't capture it in the CME2 scope, but we can still plainly see that there's something going on the oscilloscope. I'm going to bring it down to 1,000 times 10 to the minus 9 is 1e minus 5, or 10 microseconds. So on my scope, I've got it set for 5 microseconds. I have a 10 microsecond pulse there. I'm going to go down to a 1 microsecond pulse. So we can see the pulse, 1 microsecond, is triggered, and with respect to the encoder capture, it doesn't have any jitter at 1 microsecond, and the delay between the transition of the pulse and the encoder, that's a constant. So if you had a laser that needed to pulse plus or minus, nanoseconds, you could probably adjust that propagation delay. I just can't measure it on my scope here. I'm not sure what the jitter is on it. I've just run out of some bandwidth here. I will look at this in the future. We'll do multiple pulses once we hit a position. A lot of times in a linear, it's not just one position you want to pulse at. It could be multiple positions, say every 10 counts or something. So this is just a description and example of mode 0. And later on, we'll learn the other modes of operation. Thanks for watching. Okay, so we're going to look at hardware-triggered outputs. Set the high-speed output. Again, out 2 is 0x71. Out 4 for my drive is 0x73. I set it to 16 in RAM and flash. But the RAM parameters again, 185 sets the mode. So these bits define the mode. As we'll see below, we already did 0. We're going to try mode 1. There's a status register, so we can see what's going on inside of the hardware triggered at position. 87 is value 0 and 88 is value 1. 189 is the compare increment. And 1A is the time in tens of nanoseconds. So for this example, I'm going to start at position 0, and starting at some position, say 1024, a quarter way around in my motor, I'm going to start pulsing the output. So I'll set this one to 1024, I'll set this compare value to 0, and I'll set, maybe I want to pulse every 4 counts, maybe I want one every 10 counts, so that's what this 189 parameter is, and the time for the pulse. So we'll take a look at the configuration before we make the move. So getting 185, it's a value 9. 186 is some status about the moves. 187 is where I'm going to start setting the pulses. So at 1024, start sending the pulses out. This parameter I set to 0. The increment is every 4 counts, and the time is 10 microseconds. So we can see on the scope, previously I was doing 1 pulse at a position. I should get multiple pulses now after I hit this position. So I'm starting at the 0 position, my trigger's at 1024, then every 10 counts. So I'm going to start making my move, and there we go. So every time we get past that position, we'll start seeing pulses. We can't see them on the CME2 scope because they're too fast, but on the oscilloscope, we can see when this count occurs, the output fires a pulse. And when the next count occurs, it fires a pulse. So this is a B, so an A would be 4 counts per square wave here, so that's why you get 1 transition from low to high on the pulse output every time you get 4 counts. So that's mode. So looking at mode 2, this one's really boring, so I won't bother showing us, but it sets an output between 2 values. So between this value 0 and this value 1, you can turn the output on. Say between position 1000 and 4000, you want the output to be on. You just configure these 2 values. The increment setting is not used. Mode 3, single compare mode with end position. Now this is cool because let's say you had a linear motor and you want to start firing your output once you get up to speed, and then stop firing it before you start decelerating. So there may be a specific number of counts from a beginning, initially programmed in value 0, and ending with a position programmed in value 1. So this allows you to turn it off for decel and turn it on for excel. Now this node is very interesting because it talks about extrapolation. If you have an incremental encoder,
we're just reading the encoder. It's a digital circuit. It's a Verilog code that just does comparator and flip-flops and sets outputs. It's fast, and it's nanoseconds of maybe even picoseconds of propagation delay. But what happens if you have an absolute encoder? And we have to sample the encoder and then calculate the position in between the samples. Well, that's how absolute encoders work. So in this method, while we're accelerating, we do an extrapolation so that you can see there's a little bit of error based on, what's the slope when I'm starting to accelerate. But once you get to a speed, the chances are you're pretty flat with a constant speed. Your position is going to be highly accurate in between multiple reads of the position information. We close the position loop normally every 250 microseconds, or even at the current loop position update rate if we're in a current mode, but that's not very useful if you're in a position mode. So there's an extrapolation done to give us even higher positional accuracies with absolute encoders. Thanks for watching.